And then, like I said, we're going to cover sections 7.1, 7.2, and 7.3 today. Again, these are not on the chapter 6 test, which you guys are supposed to either have taken or be taking tomorrow. We will cover 7.1, 2, and 3 tonight. We will cover the next 3 sections next time. Then you'll actually have 2 weeks to test because I don't know what the testing looks like over Thanksgiving. And then we obviously won't meet on Thanksgiving, and then we'll meet the week after that. So anyway, the schedule is there in Canvas for you guys. So make sure you're taking care of business. So 7.1 is all, in fact, chapter 7 is all about radicals. Another name for radicals is roots, okay? And radicals are the inverse operation of exponents, okay? In math, you have inverse operations. The opposite of adding is to subtract. The opposite of multiplying is to divide. The opposite of exponents is radicals or roots. So for example, 5 to the second power equals 25. So then the square root of 25 is 5. So again, if we're trying to figure out 5 times itself is 25, we want to figure out what number times itself is 25. That's what this symbol is for. And again, that's called the square root. Okay, now there are a number of things we can do with this. 7.1 is primarily about perfect radicals. Perfect radicals come out to pretty little whole number answers. So we're going to talk about a few of those types of things. 7.3 deals with non-perfect radicals, so we'll talk about that. And then 7.2 deals with rational exponents. But in any case, we're going to be dealing with radicals. So the square root of 25 is 5. Likewise, the square root of 144. Again, it's asking what number times itself is 144. That would be 12. Now, this worksheet, this My Math Lab does do some really big numbers. For example, if they ask for the square root of 52,900, that's probably not something you just know right off the top of your head. The good news is your calculator will do radicals. I'm going to do my best to show you my calculator. Now, I understand that all calculators are different. You probably don't have the same one that I do, but just in case, you will have at least something similar. It'll behave in a similar fashion. But somewhere on your calculator, you will probably have a square root button. Now, on some, it's like above. So like, see how mine has some gold symbols above? You can hit like that shift or that second button to get to those upper modes. But in this case, if I wanted, say, the square root of, see if I can get to where you can see this. Of course not, it's not going to play it nice. You can kind of see that. So if mine, you hit the square root button, it gives you the radical, and we can type in that number, that 52,900, and hit equals. Your calculator should generate what that square root is. So hopefully you can figure out your calculator. You can YouTube just about anything. If not, you can email me, like show me a picture, and I can kind of walk you through how to make sure you can make your calculator work. So anyway, they're going to have you evaluate some pretty little square roots. You're going to be able to use your calculator to do so. Then they will start changing some things up. For example, all of these are square roots, and a square root implies an index of 2. So when you don't see it, it's automatically an index of 2. It means the square root. Again, that's the undoing of the squared exponent. If they change the index and did something like this is what we call a cubed root. Okay, this is undoing the third power. So what this is asking is what number times itself 3 times is 27. So again, it's undoing that third power. For example, if I told you to take 3 to the third power, that means 3 times 3 times 3. All 3 times 3 is 9, times 3 is 27. So the cube root of 27 is 3. Okay, so again, that's essentially what it is asking for. Now, your calculator will also do cubed roots like squares. It's a little trickier to find. So again, most calculators will have a square root button. Okay, also calculators will have a radical button where you can change the index. I don't know if you can see that very well. Anyway, most calculators will have a button. Okay, it's typically right above the square root, and it'll have something like an X with a square root symbol, or like mine draws boxes in there. But in any case, that allows you to change the index of your radical. So on my calculator, if I want to do the cube root of 27, okay, I hit shift and I hit my exponent button. It draws a radical up here with a place for me to change my index, which I can type in as a 3. Then I can type that 27 into my square root and I get 3. Okay. So that's going to give you some things to mess with. Now they'll do 4th roots and 5th roots and 6th roots and so on. For example, they may ask you to find the 6th root of 729, which again, that's probably not something you can just rattle off from the top of your head. Most people don't know 6th powered exponents, just a whole bunch of them. But again, using your handy dandy calculator, we can type in, again, that radical button. So I can change the index and I can type in my number, which was 729, and I can hit equals. And again, it says 3. So they're going to have you evaluate some perfect radicals. Some will be perfect square roots. Some will have a different index, like a 3rd root or a 6th root. Now, don't confuse that with a multiplier. For example, okay, these are two, obviously with different numbers, but anyway, these are two completely different ideas. If the number is basically the same size as the radical, then this is a multiplier. Okay, what this is saying is 3 times the square root of 25, which the square root of 25 is 5. So in this case, 3 times 5 would be 15. So if the number is big, roughly the same size, then it's implying multiplication. If the number is smaller and kind of above, okay, that's called an index. Okay, and it changes your root. So now we're dealing with a cubed root. The cube root of 27 is 3. So pay attention to the difference between a multiplier and an index. They will have you simplify some and they'll put a number out in front, full sized, not an index. So be aware of that. Okay, another thing they're going to deal with is negatives. There's a couple of ways they can do this. They behave differently. First off, if they just put a negative out in front of your radical, that just implies the negative of. So this is saying the negative of the square root of 4, which the square root of 4 is 2. So the negative of that would be negative 2. Okay, if they put the negative inside the radical, that causes some issues. Okay, if your radical has an even index, like a square root or a 4th root or a 6th root or an 8th root, then we do not have a number in our real number system that will multiply to get a negative number. For example, +2 times +2 gives you a positive 4. So it's not 2. But similarly, -2 times -2 also equals a +4. So it's not -2. There is no real number that you can multiply by itself and get a negative solution. So for 7(1), all you have to say is that that is not real. Okay. Now, eventually, in one of these lessons, we're going to talk about imaginary numbers, and I'm going to give you a way that we can actually do the square root of -4. But for 7(1), all you have to indicate is that it is not real, and that works for any even index. For example, if they told you to find the 6th root of -729, okay, we did the 6th root of +729, and that was 3. However, if you have a negative inside and an even index, then all you have to say is that this is not real. Now, it's a different story for odd indexes. With an odd index, like a cubed root or a 5th root or a 7th root, okay, negatives will yield a real solution, because again, this number is asking what number times itself 3 times will equal -8. And that is actually a -2, because if we take -2 times -2 times -2, -2 times -2 is 4. 4 times -2 is -8. So there is a number you can multiply by itself 3 times and get a negative answer. So anyway, odd indexes yield a perfectly fine real solution. Even indexes give you a not real solution. So they do throw a couple of those in there. And same thing, if they put a negative in front, that implies just a negative of whatever. Okay. Now, your calculator will also do this kind of stuff. So if you forget whether it's real or not, for example, if I try typing in the 6th root of that -729, my calculator says that's a math error. That's not a real solution. It doesn't know what to do with that. It won't even give you a decimal approximation. So that's a good indicator that this is not a real solution. On the other hand, if I do that same thing and I type in the cubed root of -8, and hit equals, my calculator generates a solution of -2. So if you're not sure, forget whether it's a real solution or not, again, your calculator will help with that. All right, now they do ask for the approximation of a radical. Now, again, in 7.3, which we're actually going to talk about next, I'm going to show you a better way to do this and a way to give an exact answer. But if they ask you for, say, the square root of 20, okay, 20 is not a perfect square number. There's not a whole number that I can multiply by itself and get 20. Okay, 4 times 4 is 16, 5 times 5 is 25. So somewhere in between 4 and 5. But I don't know exactly what that is. Now, depending on your calculator, if I type in the square root of 20, some calculators will simplify for you. For example, mine says the 2 square roots of 5. Okay, that's actually the simplified answer, which we're going to talk about in 7.3. But for 7.1, they want the decimal approximation. So if they ask you for the approximation, then you can just give that decimal. Now, also in my math lab, they will typically give you where they want you to round. Usually they will ask you to round to the nearest thousandth. That's the third decimal place. So that's tenths, that's hundredths, that's thousandths. So again, to round, we look at the next number. If that number is 5 or bigger, we round up. If that number is 4 or smaller, we just drop it off. So our correct answer rounded to the nearest thousandth is that 4.472. So again, if they specifically ask for the approximation, that's when you can give me that decimal. Okay, really that's only for 7.1. Once I teach you 7.3, so any assignment beyond 7.1, I'm going to want the exact answer, which like I said, which I'll talk about, and that would be 2 roots of 5. But anyway, I'll show you how to get there. But if they ask for, say, the negative square root of 17, again, and they ask you to approximate it, they'll also typically put in that symbol for the approximation of. We can type in the negative square root of 17. It equals S to D. That's my standard to decimal button. It gives me my decimal, which is negative 4.1231, which again, if we round to the nearest thousandth, again, that number just drops off. We get negative 4.123. So most of the problems in 7.1 are exact. However, there are some where they ask you specifically for the approximation. That just means the decimal equivalent. Now, they will also throw in some variables. Radicals and variables are closely related to those properties of exponents. Remember, radicals undo exponents. So when you're finding, say, the cubed root of x to the 12th power, what we're trying to figure out is if there's anything we can multiply by itself 3 times to get x to the 12th. Okay, so remember, this is closely related to those properties of exponents. If you're multiplying exponents of the same base, you would add those exponents together. So again, undoing that, we just got to figure out what number added to itself 3 times would give me 12. So this is basically just straight up division. If you divide the exponent by the index, that will give you the correct answer. So the cubed root of x to the 12th is x to the 4th. And they can do the same thing with multiple variables. For example, if they said, what is the 5th root of x to the 10th, y to the 20th, z to the 5th? Again, we just simply divide our exponents by our index. 10 divided by 5 is 2. That's an x to the 2nd. 20 divided by 5 is 4. That's a y to the 4th. 5 divided by 5 is 1. So that would be a z to the 1st. Now, again, you don't have to write the first power. Any number or any variable by itself is assumed to the first power. Now, you can put that 1 there. That's fine, but it's also not necessary. Now, this is not difficult, obviously, but the one thing they can do that tends to trick people, again, if they ask you for the square root of y to the 12th, remember, if you don't see an index, that is automatically a 2. Okay, so if there's no index visible, just a square root, that is automatically a 2. So when we divide 12 divided by 2, that would be y to the 6th. So anyway, just remember, if they don't show the index, it's automatically a 2. So make sure you're dividing by 2, not by 1 or something else. Now, the other thing they can do with this is kind of combine all of these things together. So for example, they may ask you for the square root of 81, a to the 6th, b to the 4th, c to the 8th, or something like that. All right, much like in properties of exponents, we treat whole numbers and we treat variables and exponents differently. So we're going to treat this like it is separate problems, even though it's all one problem. So if we take the square root of 81, so if I can like kind of block that out for a second. So if we just look at the square root of 81, just the whole number part, all right, the square root of 81, well, that's 9. So then if we look at, okay, the variables and the exponents, okay, remember with a radical with no index, that's a square root. So then we just divide. 6 divided by 2 is 3. 4 divided by 2 is 2. And 8 divided by 2 is 4. So if they combine whole numbers and variables and exponents, you should be able to simplify those. Fractions is also something we don't need to be scared of. If they give us something like the square root of x the second over 16 y to the fourth. This is like saying the square root of x to the second over the square root of 16 y to the fourth. So we can do all of these things. So again, square root, if you don't see the index, it's a 2. And again, exponents and variables divide. 2 divided by 2 is x to the first. The square root of 16 is 4. And again, variables and exponents divide. 4 divided by 2 is 2. The correct solution to the square root of x squared over 16 y to the fourth is x, or x to the first, over 4 y to the second. Now, the last thing they have you do, and they just throw this in kind of all willy-nilly in this section, is they have you look at the graphs of a radical function. So just real quick. The graph of a square root function kind of looks like this. So if we can't plug in negative numbers because they're not real, but if we just make an XY chart, okay, if I plug in 0 into x, the square root of 0 is 0. If I plug in 1, the square root of 1 is 1. If I plug in 4, the square root of 4 is 2. If I plug in 9, the square root of 9 is 3. The way we can plot that, we get 0, 0, 1, 1, 4, 2, 6, 7, 8, 9, 3. The graph of a square root function kind of looks like that. Now, they may also ask you about the domain of the function. Well, that's easy enough, especially if we look at the graph. Well, that can't be anything negative. So your domain, your inputs, is anything from 0 on, using that interval notation. So the domain of this function would be like so. Now, if they give you some kind of alteration to that function, for example, if they wanted you to do something like this, okay, f of x equals the square root of x plus 3 minus 2, relatively easy. These just shift your graph. So it's going to be this same graph. You're just going to change the location. You're going to shift it up and down and left and right. Okay, the number inside of the radical, we'll shift it left or right. This one also moves backwards to what you would think. So a plus, we'll shift it to the left, while a minus will shift to the right. Anything being added or subtracted outside of the function will shift the whole thing up or down. This one moves like it's supposed to, so a positive will go up and a negative will go down. So this particular function will take this exact same square root function and we'll shift it 3 units to the left and then 2 units down. So this 0, 0 would go left 3 and down 2. So now this point is essentially right here. Otherwise, it's the same graph. So over 1 and up 1, 2 over 4. So it would look like that. So then again, if they ask you about the domain of this particular function, okay, it's everything from -3 forward. Now, if they talk about a cubed root function, that's different. Okay, whoops, cubed root, not cubed. A cubed root function. Now remember, you can do negative inside of a cube root. The negative here with an odd index gives you perfectly good solution. So a cubed root function looks more like that. So the domain of a cube root, because we don't have any limiters, we can do cube roots of negatives. The domain for this particular function is all real numbers. Anyway, we're not going to do a whole lot with the graphing, but they did throw a couple of problems in my math lab, so I at least wanted you to have a chance to look at that. So again, 7.1 is primarily about perfect radicals and simplifying those. And I'm actually going to jump a bit. I'm going to go to 7.3, and then I'm going to come back and address 7.2. So 7.3 is all about simplifying non-perfect radicals. Now, if I give you a non-perfect radical, or if my math lab gives you a non-perfect radical, so after 7.1, I no longer want the decimal approximation. I'm going to want some exact answer. I'm going to show you how to go about getting there. So for example, if I asked you for the square root of 48, some of your calculators, if you type in the square root of 48, it will generate the decimal solution. For example, if I type in the square root of 48, some of your calculators will give you that 6.928. Again, that's not what I'm looking for here. With 7.3, I want exact answers. Now, some of your calculators will actually generate the simplified answer. If you type the square root of 48 into your calculator, it may tell you 4 square roots of 3. If that's the case, that's what we're looking for. Now, just in case your calculator doesn't do that for you, I will walk you through how we get to these numbers, or what this kind of even means. And there's a couple of ways to do this, and I'm going to show you what I call the tree method, or the prime number method. So one thing we can do is we can break 48 into its prime factors. Basically, to do that, all I got to do is figure out any numbers that I can multiply to get 48. Okay, so 48 is 2 times 24. Now, 2 is what we call a prime factor, because prime numbers can only be broken down into itself and 1. So obviously writing 1 and 2 a whole bunch of times doesn't help me out. So once I get a prime number, I can stop. Now, 24 breaks down again. 24 is 2 times 12. 12 is 3 times 4. Now again, 3 is a prime number because the only thing I can multiply to get 3 is 1 and 3. 4 is 2 times 2. Okay, so what this shows is these are all of my prime factors. These are the numbers I can multiply to get 48. Now, this isn't the only way we could have done this. Like, we could have divided by 3 first, or we could have broke this up into 4 and 12. Anyway, you can break this up in a bunch of different ways. Okay, so when we do so, when we get to our prime numbers, what we're looking for with a square root, we're looking for pairs. If I have a pair of numbers, that goes outside. Here I have another pair of numbers. That also goes outside. And then any number that does not have a pair stays inside of the radical. So obviously, if you have multiple numbers, we can multiply them together. 2 times 2 is 4. So the simplified form of square root of 48 is 4 square roots of 3, just like I said. Another example. Let's say we wanted to break down the square root of 90. So again, 90, I would do 9 times 10. 9 is 3 times 3. Those are prime. 10 is 2 times 5. Those are prime. So if a number can be divided by anything other than 1, we need to break it down. But if it can only be divided by 1, then that's prime. We want to break a number into its prime factors. Then again, for a square root, we're looking for pairs of numbers. If we have a pair, that goes outside of the radical. Anything left over with nobody, with no pair, goes inside of the radical. Again, if you have multiple numbers, we multiply those together. So the square root of 90 is 3 roots of 10. Now, like I said, some calculators will do that for you. If I type in the square root of 90, my calculator generates 3 square roots of 10, just like I got. So that's something they could ask you to do. They can also do the same thing for non-square roots. They could do something like, oh, I don't know, the cubed root of 54. Okay, the difference is if we change the index, what that changes is what we're looking for. So we still do the prime factors, which 54 is 9 times 6. 9 is 3 times 3. 6 is 2 times 3. Okay. With a square root, we were looking for 2 of a kind. So guess what we're looking for with a cubed root? We're looking for 3 of a kind. If you've got 3 of any one number, now that comes outside. And then whatever is left over, anything that does not have a buddy to go with it, stays inside. Now, it is important that whatever index you start with, like a square root, your answer will have that same index, a square root. This one started with a cubed root, so we stay with a cubed root. So don't just drop your index off. Okay, now, like I said, with my calculator, it does square roots just fine. If I type in the square root of 90, okay, it generates 3 square roots of 10. That's pretty cool. But even my calculator won't do cube roots. If I type in the cube root of 54, my calculator jumps straight to that decimal approximation, which again, that's not what I'm looking for. I want the simplified form. So you've got to go through the long way to get there. Okay, now, sometimes they will do something like this. This looks like any other problem. This is a 4th root. I'm not really good about doing 4th roots in my head, so I'm just going to go ahead and try to break this down. So I'm just going to take that 2,401 and I'm just going to use my calculator and try to find anything that it's divisible by. So if I try dividing by 2, I get a decimal, so nope. 2401 divided by 3, that's a decimal, so nope. 2401 divided by 7, aha. Okay, that's 7 and 343. 7 is prime. So again, divide. That's 7 and 49, which 49 is 7 and 7. So again, we can still break our number down into its primes if we have a fourth root. That tells me I'm looking for 4 of a kind. If I have 4 of something, that goes outside. But wait a minute, if I don't have anything left over, then I don't have anything inside of the radical. So what that means is this one was actually a perfect root. The fourth root of 2401 is 7. So if you're breaking it down and all of them, okay, give you what you're looking for and you don't have anything left over, then what you had was a perfect radical. Okay, it didn't end up giving you anything left over. So with nothing left over, there's no radical piece. It's just a pretty little whole number answer. Okay, same thing. Say I needed to simplify the cubed root of 60. All right. 60 is 6 times 10. 6 is 2 and 3. 10 is 2 and 5. This cubed root tells me I'm looking for 3 of a kind, but I don't have 3 of any one number. So what that tells me is none of these things break down. So they all stay inside. So 2 times 3 is 6. 6 times 2 is 12. 12 times 5 is 60. So this one is simplified. It actually doesn't break down. So sometimes everything will break down and you'll get pretty little whole number answers. Sometimes nothing breaks down. This is considered simplified. So just be aware that they can do that. Now, the other thing they will do with this is they're going to start mixing in variables and exponents. Again, same process. Just now it's probably not going to divide in quite so evenly. So if we need to simplify the cubed root of x to the 4th, again, it's division, but kind of think old school elementary division where you had division and remainders and stuff like that. So 4 divided by 3, or another way to say this is 3 goes into 4 one time, but you have 1 remainder. So any remainders are what stays inside of your radical. So the cubed root of x to the 4th, 3 goes into 4 once with 1 left over. So the simplified form of the cubed root of x to the 4th is x, cubed roots of x. Okay, same thing. So if we had the square root of x squared, y to the 5th, z to the 6th. Okay, remember, if there's no index, it's automatically a2. 2 goes into 2 one time evenly with nothing left over. 2 goes into 5 twice with 1 left over. 2 goes into 6 3 times evenly. So the simplified form of the square root of x squared, y to the 5th, z to the 6th is x, y squared, and z to the 3rd. Okay, and they could combine those two concepts and do something like the cubed root of 64 x cubed y to the 5th. Again, we're going to kind of treat this like it's 2 different problems. We're going to do the whole number piece, then we're going to do the variable exponent piece. So again, 64, we're going to break into prime factors. 64 is 8 times 8. 8 is 2 times 4, which is 2 times 2. 8 is 2 times 4, which is 2 times 2. Okay, again, we're looking for groupings of 3. I get a group of 3 that goes outside. I get a group of 3 that goes outside. Variables and exponents. 3 goes into 3 once with none left over. 3 goes into 5 once with 2 left over. So then if we clean this up, 2 times 2 is 4. We can't combine any of our variables. So we end up with 4x y times the cubed root of y squared. And again, pay attention to the fact that if my index was a 3, I keep my index of 3 with my answer. Okay, don't just drop that off. And if they would have put a negative outside, that would just make your answer negative, so just be aware of that. 2, they'll try to mix that stuff in as well. I'll do one more example of like this, so you have something else to look at. We'll just do a simple square root 1. So let's say we got the square root of 50 x y to the cubed z to the 4th. So again, we're going to treat this like it is separate problems. 50 is 5 times 10, which is 5 times 2. Again, that pair of numbers goes outside. Anything left over stays inside. I'm leaving space because I've still got to deal with my variables. 4 markers starting to die. Okay, again, with variables and exponents, if you don't see an index, it's a 2. Okay, if the exponent is smaller than the radical, obviously it doesn't divide in. 2 doesn't go into 1. So that x to the first is just going to stay inside. I can't bring anything out. Now, as long as the exponent is bigger than the radical, then we can divide. 2 goes into 3 once with 1 left over. 2 goes into 4 twice. So in this case, my solution is 5y z to the second times the square root of 2xy. And that's basically 7.3. So 7.3 is going to be about simplifying radicals. Some will be perfect. Most of them are not. That's something you should be able to do. All right, last but not least, 7.2. 7.2 is all about rational exponents. Okay, rational exponents, another word for rational is fraction. So basically, this is just going to say that fraction exponents is just another way to write a radical. For example, the 5th root of x to the 2nd power is the exact same thing as x to the 2/5 power. Okay, so rational exponents is just another way to write roots or radicals. Okay, that index number becomes the denominator of your fraction, and any exponents here go to the numerator. So again, the 5th root of x squared is the exact same thing as x to the 2/5. They're going to have you work back and forth between notations. They're going to say, hey, write this as a fraction exponent. Okay, do so. They'll give you this and be like, hey, write this with radicals. Okay, there we go. So you should be able to write radicals as exponents and write exponents as radicals. The trickiest thing they can do with this is they can give you something like, okay, where some of your numbers are again implied and or hidden. For example, if you don't see an index, remember a radical with no index is automatically a square root. And likewise, if you see a variable with no exponent, that's automatically a 1. So if we rewrite this as fractional exponents, that's x to the 1/2 power. And then that would be a y to the 3/2 power. Okay. So rewriting exponents as radicals and radicals as exponents are going to have you go back and forth between the two. Now, they will also have you do some evaluating, which is really nice because if they just give you numbers and ask you to evaluate, for example, if they want you to take 27 to the 2/3 power, you can quite literally just type that into your calculator again. So I'm going to type in 27. Here's my exponent button. And I can type in 2/3. And I can hit equals. And my calculator will do it. Okay. It'll just figure out what the solution is. Now you can also do this as the cube root of 27 squared, and you can use your calculator to do that too. So I can do, again, using my calculator, I can do the cube root of 27 to the 2nd power, type that in, it's also 9, okay? But your calculator can evaluate fraction exponents as easy as it can evaluate radicals. So if they give you something like this, you can totally use your calculator to evaluate. Now, where it gets tricky is they're going to start combining numbers and variables. And also remember, with variables, we have to remember those properties of exponents. Okay. Remember, if we're multiplying, the shortcut is to add those exponents together. Okay. If we're dividing, we can subtract those exponents. If we're taking a power to a power, we can multiply. And also remember that negative exponents switch things from top to bottom or from bottom to top. So this is a couple of chapters ago, but we did all of this stuff. But they're going to have you do some stuff like this. All right, so if we've got something like this, remember whole numbers and exponents play a little bit differently. So this 25 x to the 4th to the 1/2 power means 25 to the 1/2 power and x to the 4th to the 1/2 power. Whole numbers we can do, and again, 1/2 is the same as square rooting, so 25 to the 1/2 power is 5. If we're taking a power to a power, we can multiply. And then this 5x to the 3rd, we're not doing anything else with that, so it just stays on the bottom. And again, we can simplify this. So again, if we look at that, 5 divided by 5 is just 1. If we subtract our exponents, 2 minus 3 is -1, so we get 1x to the -1, but again, we can't leave negative exponents, so that sends it down to the bottom. So we get 1 over x. So you got to remember those powers of exponents. They're going to ask you to simplify some of those problems. Goodness. Yeah, my black markers are basically dead. All right. Okay. Again, they're going to ask you to simplify. Then pay attention to your answer, because sometimes they'll ask for rational exponents. Sometimes they ask for radicals. So just be aware of that. If they want rational exponents, they will ask for positive rational exponents. So do not leave your answer with negatives. Negatives just switch down to the bottom. But in any case, so even if they give you fractions here, all of those same properties still apply. So all they're asking you to do is, again, if we're multiplying, we can simply add those exponents together. And then if we're dividing, we can subtract. So this is x to the, so 1/3 plus 2/3 is 3/3. Subtracting a negative is adding. 3/3 plus 1/3 is x to the 4/3 power. So again, if they want positive rational exponents, this is what I'm going to end up with. If they ask me to write my answer as a radical instead of with positive rational exponents, remember, this number is your index. This number is your exponent. Now, another thing they can do to trick you is to catch you when you're not paying attention. So the difference in these two things. Okay, so again, they'll ask you to write this as a radical. So again, what they want you to do is take this rational exponent, change it to a radical, which is all fine, not too difficult. The trick is, remember, when you've got parentheses, that groups all of these things together. So both of these things are being taken to that 1/2 power. So again, that's my index. That's my exponent. That's 2 to the first and then x to the first. So if we clean this up, that's just the square root of 2x. However, if there's no parentheses, what's the only thing being taken to this 1/2 power? Okay, just the x. In this case, this is 2 times x to the 1/2 power. So if there's no parentheses grouping these things together, then that 2 is unfazed by that radical. So this one would end up being 2 square roots of x. Now, if you're doing a power besides 1, you need to pay attention to grouping symbols as well. For example, if they told you to take 4x cubed to the 3/4 power, again, in parentheses, what we're saying is the 4th root of 4x to the 3rd power. Now, sometimes in my math lab will let you keep it like this. I would probably have you go ahead and FOIL this, or not FOIL, but take these to the powers. So that's 4 to the 3rd power. So 4 times 4 times 4, 64. And then x to the 3rd power would be x to the 3rd. Okay, but remember, when you've got grouping symbols, again, you're taking all of these elements to those powers. All right, that finishes up the first 3 sections of chapter 7. Again, about a handful of you have already tested over chapter 6. Good job. The rest of you that haven't, make sure you get that done. It's only scheduled to be available for one more day. For some reason, like because of the internet outage, if you couldn't get in, let me know. I'll try to extend it, but I can't make any guarantees. You've had this whole week to get that test done. So make sure you take care of business there. That being said, stay on top of your homework. Make sure you're doing your homework for chapters 7. Now 7, 1, 2, and 3 are live. You need to work on those. Next Thursday, we will cover the last 3 sections of chapter 7. Then we're off for Thanksgiving break, and then we've got 3 more sections to cover of chapter 8, and that's basically it. Then all we've got left is the final. So the end of this school year is, or the end of this semester is rapidly approaching. Make sure you're taking care of business. So anyway, that's all I've got for you. If you have questions, stick around, ask them. I'll do my best to answer. If not, you are free to go.